All right, so we're all set to start Module 3. So let's just do an overview of what's out here right now. You're going to notice that in our learning plan, kind of have all the sections and the practice problems that we're going to be going through. I do have our PowerPoint for Chapter 3 here. That's going to be guiding us in our lecture tonight. You'll also notice that there'll be session recordings. Once I record them, this is the first time that they'll be out there. And then you'll also notice that I have our practice problems and our application problems. So practice problems, we're going to have 3 for each one of the chapters, 3 for chapter 13, and then 3 for chapter 17. So we'll be getting through the chapter 13 ones this evening. And then application problems, you're going to notice that looks like we have 4 from chapter 13 and it looks like 3 from chapter 17. So you'll notice here that I have the answers and also the page that you're going to find them on in your McGraw-Hill textbook. So you won't want to start those until after we've kind of done some of these practice problems that are going to help you get prepared for those. So let's open up and look at our Module 3. And I'm going to kind of scooch out here just a little bit so we can see. So as we look at this chapter is really broken into 2 sections. We're just going to be doing the first part now, and then we'll be coming back to chapter 13 later in the term. But this chapter is really about energy and momentum. And the first part that we're going to be talking about in chapter 13, which is going to be the first section, is going to be the energy portion here. Now, previously, we've done a lot of problems where we have set up our problems to be sum of the forces is equal to mass times acceleration. That's that second Newton's law that we've been using in applications. But we're going to find that as we expand on that a little bit, and we're not violating anything, but we're going to see that there are going to be opportunities for us to use the work energy theorem. That's what we're going to be looking at here today when we are trying to find different types of variables. So as we look here, when we are looking, for instance, and we're interested in forces and accelerations, Newton's law gets us usually what we need. But if we're more interested in and need to find maybe velocities and displacements, now we're going to be looking at like the work energy connection. And then velocities and times are going to be the impulse and momentum. So like I said, we'll be getting to that a little bit later. So we're going to be focusing really in this chapter 13, this beginning of chapter 13, right here in the middle is going to be the focus of what we'll be applying for the problems that we have. So work of a force. So forces are going to perform work, and work is basically going to be exerting a force through a distance, okay? And that's the very basic definition of work. So there are a lot of things that sometimes we think we're doing work, or it feels like we might be doing work, but we're actually not. And I like to distinguish work and thinking of work in terms of when I look at the force that I'm kind of analyzing, how can I say this? If I'm looking at a force, does the distance that is being looked at, is it over or in the same direction of that force? So for instance, if I'm pushing a crate, my force has to be parallel, or if you would, horizontal, so that it can push along the floor. Okay, so my distance and my force, I like to say, are in the same direction. But if I am lifting a package and I'm walking with it across the floor, no work is being done because the package has weight and its force is vertical, but I am moving horizontally. So no work is done on that. I might feel it in my muscles. There might be work being done there. But as far as work being done on that package by me, I'm not doing any work. Does that make sense to everybody? If I was lifting the package vertically, like from the floor and putting it onto a table, now work is being done on that package because now the distance that I'm exerting that work through is in the same direction as the force, okay? So this is a nice list of things that are not work. And so, because sometimes you look at forces, oh, there must be work being done. Not all the time. It depends on the distance for which that's the force is being acted through. So a reaction at a frictionless pin supporting a rotating body, no work is being done there, all right? Reaction at on a frictionless surface where the body in contact moves along the surface. Reaction at the roller moving along a track. And the one that I just mentioned is going to be this one, is the weight of a body when its center of gravity moves horizontally. So that's that package that I'm holding and I'm walking with it horizontally, but its weight is actual vertical. So we're always looking for that force and the distance for which it's being applied to be in the same direction. So if I have a horizontal force, I'm looking for a horizontal distance. If I have a vertical force, I'm looking for a vertical distance in order to calculate work. The next thing that they're looking at here is going to be power and efficiency. So power is simply going to be force, and we can multiply it by how fast that's going. So, so as we look here, some common terms and common units for power are going to be the watt in the metric system, and then horsepower in the English system. And then lastly, you're going to notice down here that we have a little bit of efficiency. So they're looking at how much output work is there actually going to be, and then we're going to divide it by how much work we actually put in. So we should see, ideally, you want to have high efficiencies. No efficiency can be more than 100%. So anything that says that you're getting 150 efficiency really is not possible, right? As we know, typically we're trying to get efficiencies of 80, 90% if we're lucky. So because there's always going to be losses, in that system as things move. So the next slide that I have here, we're moving into our sample problems. But what I want to do before we go there, what I'd like to do is just kind of do a little review of the equations. They weren't very comprehensive in the PowerPoint here, so I want to do that before we start looking at our problems. So I'm going to go underneath my camera here, and we're going to create an equation sheet for this chapter, because there is a set of equations that we'll be focusing on. That doesn't mean that we're not going to use equations from previous, and that's why it's good to kind of have this running list of different equations. I have a couple pages here that I pull out. Yes?
You call it work equations?
I'm calling it chapter 13 equations, because there's work, there's going to be energy, there's going to be power, there's going to be, units for those things. So I'm going to call this chapter 13 equations. Okay. All right. So the first one that we're going to look at, and this is a new book to me. All right. And I've taught physics, as you know, in my previous job. And we always refer to work with a capital W, which I think is very common. All right. But this book doesn't. So they use the variable capital U. Okay. Capital U is going to be equal to force times distance. What was that? I agree, but I want to be consistent with the book, because otherwise you're going to see, two different things going on here. So over on the right-hand side here, I'll kind of put the variables. So U is equal to work, okay? F is going to be equal to force, and then our D is equal to distance, right? Oops, I work, not word, work. Now, standard units here, because we have force times distance, these units are going to be, for instance, pounds times feet, right? Or they could be newtons times meters, are going to be very common, all right? And if we're in the metric system, they call that a joule. A newton meter is a joule. So if in fact you get something given to you in the units of joules, that's a Newton meter. And sometimes we got to expand that out in order to do the cancellations and such, okay? All right, so that's going to be work, all right? Now, there's a work energy theorem, but before we get there, let's talk about kinetic energy, okay? It's going to connect work and kinetic energy, but let's look at kinetic energy, and here's another one that they did a switcheroo on the variable. They're using T for kinetic energy, capital T. No, nope, you're going to have to use T. I need T. Yeah, I need you to do that. Or KE is usually the one that you use. Yeah. So, but T is what they use here. So T is going to be equal to 1/2 mv squared. Okay, so the second part should be pretty familiar to us, where T is going to be equal to kinetic energy. Okay. M is going to be equal to mass, and V is going to be equal to velocity. Okay. Now units here, okay, are also going to be in pound feet. They're the same units as work, pound feet for English. Oopsie. And they're going to be Newton meters or joules for the metric system. Okay. Oops, here comes John. Now, work energy theorem. Work energy theorem basically lets us know that if there is a change in kinetic energy, that means that it was brought upon by an external force or there was work done on the system. So we can say the amount of work that was done is going to be equal to the change in kinetic energy. Okay, you've probably heard that before in your physics classes. Okay, so that relationship is going to be U, and we call it 1 to 2 because when we talk about a change in kinetic energy, that refers to like a position or a state number 1 as opposed to or over or to a position or a state number 2. Okay, so kind of like a before and an after. So that's going to be equal to change in T, which is equal to T2 minus T1, where T2 would be the ending state, T1 would be the beginning state. All right. You also see this very often where they eliminate the negative value here. So this can be, I'm going to kind of put 2 arrows down here just to kind of rearrange, if you would, T1 plus our work. So our kinetic energy 1, T1 plus U 1 to 2, our work 1 to 2 is going to be equal to T2. So it's just an algebraic rearrangement, but we see it like this quite often. Okay, this is kind of like the form that we're going to see the book use a lot. Bless you. Bless you. Now, the units on either side, as you can see, we can combine those or we can set those equal to each other because indeed the units are the same. Okay, so it's going to be important as we start our problems that we get things in common units like pounds, feet, Newton, meters, whatever the system is that we're in, so that we can ensure that we end up with the correct units in the end. Okay. The next one that I have here is going to be power. Okay. So P is going to be equal to W over T.
That's time though.
U, yeah, it is.
I wrote that.
U, sorry, I have a W here because that's like my normal. It's U, it's work over time. It's how fast do we do the work? So for instance, if we look at power and we think about carrying like a box up a flight of stairs, if I run up the stairs, it's going to take less time. So that means I'm gonna need more power to do that. If I walk up the stairs, it's going to take more time and I'm not going to need as much power. So at the top, you can probably feel you're more exhausted. You've used more power, if you would, if you ran up the stairs as opposed to just walking up the stairs. So that's kind of a difference in power, if you would. We can also find it using force times velocity. Okay. Both of them are going to give us the same value. Now, there is going to be a conversion that's going to come in handy. And that's 1 horsepower is equal to, I'm having a hard time here, 550, and this would be foot-pounds per second. Okay. Or pound-feet per second, foot-pounds or pound-feet per second. So this is just a conversion, okay? Because we'll usually get our work or our power in foot-pounds, and then it's going to be per second. But then we usually express it in the English system in horsepower. So you'll usually see final units for power as horsepower in the English system. In the metric system, it's the watt, okay, W. And I always like to write out the watt, okay? And maybe this is why they changed it. I get it. I always use capital W for work, but then you'd always come upon power, and the units for power were the watts. So you'd have to kind of watch your variable with your units and make sure that you weren't kind of crossing over. So maybe that's why they did it. So that's going to be the SI units for a watt or for power. All right. So that's what I have on my equation sheet. I think this is a good start. You can certainly customize that and make it what you want. So as we go through problems, if you find that you want to add some notes to it, obviously that is yours for your eyes only. And I think we're ready to get into it. So chapter 13. Let's look at our first sample problem. So I'm going to go back to our PowerPoint because it usually has a little bit nicer illustration here rather than going underneath the camera. But it says here that we have an automobile that's weighing 4,000 pounds, is driven down a 5-degree incline at a speed of 60 miles per hour. Okay, 60 miles per hour. When it brakes, when the brakes are applied, causing a constant total braking force of 1,500 pounds. Determine the distance traveled by the automobile as it comes to a stop. Okay, so how long will it take it to come to a stop with that braking force at that incline? So let's kind of get set up here. Oops. And start here. This is sample problem 13.1. So this is your first practice problem that you are going to be handing in. I'm going to use our convention here. Things going to the right and up are going to be positive. Now, the information that's given to us in this problem, we know that the weight of the car is 4,000 pounds. We know that it's velocity 1. So previously they were calling it velocity 0, kind of like original state. Now in this chapter, because they've gone to kinetic energies 1 and 2, now they're calling it velocities 1 and 2. So 1 is just an initial state of the velocity, and that is specified at 60 miles per hour. That's how fast we're going when we step on the brake. And then we have a braking force, a constant braking force of 1,500 pounds. Okay. Now that's a constant braking force, so we would expect constant acceleration as well, / deceleration, because we're slowing down. Now we want to find, the distance traveled. And I'm going to call that D. Okay. Now, as we saw on our slide earlier, so I'm going to kind of go back to that previous slide. I really like this. We are looking for a displacement, which is a distance. That is why we're going to be focusing on the work energy theorem here, because work has that force times distance in it. That gives us a direct relationship to the things that we're doing. So, so that's why it's kind of in this section, and that's why we're going to be using that that work energy theorem. So what I'm going to do up here is I'm just going to remind us of that equation. T1 plus work 1 to 2 is going to be equal to T2. Okay. Now there's two parts of this equation. There's kinetic energy, 1 and 2, and then there's the work. So what we're going to do is we are going to look first at the kinetic energy of position 1. Okay. And then we're going to look at the kinetic energy of position 2. And then we're going to look at the work part of this equation. So kind of break it down, into their separate parts, if you would. Okay, so let's look at the kinetic energy. Okay. And this is going to be for position 1. And that's going to be like when we start braking. Okay, that's going to be when we start braking. So we can say T1 is equal to 1/2 mv1 squared. Okay. Now, this velocity is going to be our 60 miles per hour, but as we know, we need to have this in our English units. So this needs to be in feet per second. So we're going to now convert that. So we're going to have V1 is equal to 60 miles per hour. And we need to convert that to feet per second. So we know that 1 mile is equal to 5280 feet. Oh, 1 hour, 3,600 seconds. I'm going to squeeze it in there. So if we multiply that out, what do we get for our velocity? 88 feet per second, right? 88 feet per second. So that's the velocity that's going to go in here at velocity number 1 in our equation. So this is going to be equal to 1/2. Now this is mass, okay? Mass is equal to weight divided by gravity, right? If we rearrange our equation. So we need to take our weight, which is 4,000 pounds, and we're going to divide that by 32.2 feet per second squared. We don't need to put the units in here. I'm breaking my rule. It's hard for me to do that. I always want to put my units in. So that's going to be the mass, and then we're going to multiply by 88 feet, and we're going to square that value, okay? So what do you get for your T1? Pull the chat box out, so if you're virtual and you want to chime in, you are welcome to.
Almost like this is 0.
I got 480,994. Yeah, okay.
Do you care about rounding? Like, do you look at rounds if it's not good?
The book, I care at the end. So for instance, I like to hold more significant digits inside my problem. Now we're talking 480,000 pound-feet. I don't need decimals on this, but I held it to the pound. All right. That way I'm just more accurate in my calculations as I go through, and then I round the last answer. So when, use your best judgment when you're comparing your final answer to what the books are, because remember, they're using 3 significant digits all the time. Okay. But okay, so that's position 1. That means that that's the kinetic energy right before we start to apply the brakes. Then position number 2, okay, this is going to be our kinetic energy number 2, 1/2 the mass times velocity 2 squared. Now, here we end up at a stop, right? So what's our velocity 2? 0, right? So this goes to 0. So our T2 is simply 0. Okay. So that is the T1 and the T2 for our equation on top. Now we want to look at the work, okay? We want to look at the work. Okay. Now we know, in general, our work is going to be equal to force times distance. Now this is just a general equation, all right? We'll expand on that in just a little bit. And we want to put a plus or minus in front of here because that's going to be dictated by the direction of the force, okay? Because if there's multiple forces, we have to add and subtract them along, the direction that we're looking at. So let's kind of look at our block, if you would. So, or not our block, our car that's going to be simulated as a block. Now I'm going to exaggerate our 5 degrees a little bit on my illustration here, just because so we can see it a little bit better. Okay. This is going to be 5 degrees. And I'm going to simulate this as a block, our car, instead of trying to draw out the car. Okay. So it's going to be a block. I know that this is going to be my center of gravity. And I know that the weight is 4,000 pounds. The way this looks. I'm going to grab my straight edge. I was using it before. There we go. 4,000 pounds at the center of gravity. All right. Acting down. Now, as this is going down, so again, this is a car, it has wheels. We know that there's a braking force, and that braking force is going to work, if you would, in the opposite direction of motion. So my motion is going down the incline, right? And my braking force, B, is going to be equal to 1,500 pounds, right? And that's this force right here, opposing the motion. I know that there's a normal force, right? I know there's a normal force, but that normal force isn't doing any work, but we'll show it because it's there. But that normal force is not doing any work. Okay. Now, there is a force going down the actual incline, and that's going to be the component of the force of 4,000 pounds, the weight of our car. So to find that, what we're going to do is we're going to kind of extend our force down. I'm going to kind of make a dotted line here. Okay. And I'm going to draw kind of a perpendicular line here. Okay. Now, what this does is I'm going to draw a line parallel here. Here is our 4,000 pounds coming down. I'm just pushing it along its line of action. I know that this angle right here, this is 5 degrees right here. Okay. That means that this would be 85. Okay. This is going to be FWT. I'm going to call it the component of the force from the weight of the car. Okay. Now, to calculate that, I can use a little bit of trig, right? I can say FWT, which is that little component right here. It's going to be equal to the sine of 5 degrees, right? Times 4,000 pounds. So the weight of that car, like going down that incline, it's going to be 348.6 pounds. Sorry, not degrees, pounds. Okay. This is kind of a little separate little dealio. Okay. Now, when I look at the forces that are really affecting the amount of work, it's going to be in the direction of motion of that car, right? So it's going to be along the incline here. Do you see that? So if we kind of tip our axis system, our positive direction is going like down the incline. Do you see that? It's kind of like, here's our XY right here, Y and X. So positive, if you would, is going down the incline. All right. So now what we want to do is we want to simply kind of expand on our work equation over here. So we can say that our work is going to be the force times the distance of the braking force. Now, since the braking force is opposing motion, it is going to be a negative 1,500 pounds times the braking distance. Okay, we don't know what that is yet. I knew I was going to interfere here. And then if we're going with the positive direction here, which is going to be the weight of the component of the weight of the car going down, this is going to be our FWT, which is 348.6 times that same braking distance. See that? Okay. So we can solve for D then. So we can say, all right, U1 to 2, not really solve for D, but it's going to be work in terms of D. It's going to be negative 1151.1 D. Okay. And that's going to be your work portion of that equation. This is going to be our kinetic energy, and that's going to be the work. So now that we have both of these elements, we can go back up to our work energy theorem, and we can plug these values in. So it's going to kind of go like this. Switch this on. So T1 plus U1 to 2. So the kinetic energy at our position 1 plus the total amount of work is going to be equal to T2. So we know that T1 from up here, we're going to say 480,994 pound-feet plus, actually minus, because it's a negative 1151.1 D. It's going to be equal to T2, sorry, which is 0. We know that to be 0. So now we're simply going to put the 1151.1 D on the other side. So we're going to have 480,994 is equal to 1151.1 D. And solving for D, we're going to get 418 feet. And that's going to be our braking distance. Okay. So questions on that one? It's kind of a cool little problem, right? All right. Then the next problem that we're going to do is going to be 13.2. But what I'm going to do is I'm going to break this up into different recordings. So I'm going to stop the recording here after 13.1, and then we'll start the recording again for our next sample problem.